The fifth problem is on the hydrogen atom. So we are given that the del squared operator, the grad square operator in spherical polar coordinates is given by the following expression. So this is in the spherical polar coordinates. It is very easy to write it down in the Cartesian coordinates, but this is in the spherical polar coordinates. We need to verify that the wave function psi as a function of r, theta and phi in the spherical polar coordinates given by 1 over square root pi a naught cubed into exponential minus r over a naught is an eigenfunction of the hydrogen Hamiltonian with m equals m naught if a naught is given by the equation in 3.65. So this is from the text. In the text, equation number 3.65, I'll write it down for you. And then we need to find its energy. Verify also that the wave function is correctly normalized. So this is equation 3.65, which gives the expression for a naught, which is 4 pi epsilon naught h cross squared over m naught e squared. Now this a naught is nothing but the Bohr radius. Okay, so this is the question. We are given the wave function for the hydrogen atom and we need to verify that this wave function is normalized, and also we need to find out the energy, and we need to see whether this wave function is indeed an eigenfunction of this of the hydrogen Hamiltonian. Now for hydrogen atom, we know that the atomic number Z is equal to 1. And the Hamiltonian for any hydrogen-like atom, not just hydrogen but hydrogen-like atom, which means single electron, is given as follows. This is the grad squared operator. So this is the Hamiltonian, and here Z equal to 1. So this will become 1. And psi is a function of only r in our case. So this means that the component of grad squared in theta and in phi are both 0. That means this term, this component in theta and this component in phi, both of these are 0. So I can highlight it. So this is theta component right over here, and this is 0, and the phi component, this is this, and this is also 0. Okay, you get the point. Now let us come back to our Hamiltonian. So first let us look at the first term in the Hamiltonian, this term right here. So grad squared psi, and only the term in the r component will survive. So we have 1 over r squared del over del r squared del over del r of psi. And psi, let us for now just take this exponential term, that additional term 1 over square root pi a naught cubed is just a constant. So the derivative will not affect the constant will remain as it is. So let us for now ignore the constant. The constant will just come out of the derivative. So derivative of exponential remains the exponential and the coefficient comes out. Let me write it in the next line. Sorry, there's this minus sign comes over here, so this minus sign is there. Now we will use chain rule of differentiation. So derivative of a product of function is first function times derivative of second function plus second function times derivative of first function. So this is first function times derivative of second function plus derivative of first function times the second function. That this is according to the chain rule. So this, as we see, is just our wave function psi. We had not taken the this constant term, so that's why the constant term is not here. So had the constant been written, it would be there as a coefficient. So now let us look at the Hamiltonian H psi. Del squared psi, so this is grad psi we just evaluated. Again, we will not write the constant term, it's just a constant which is common to all the terms. Now for this H psi to be equal to E psi, which is the Schrodinger equation, and this is also the eigenfunction or the eigenvalue equation, where psi is the eigenfunction of Hamiltonian and E is the eigenvalue of the Hamiltonian. So for this to be equal to E, it's like a constant times psi, what we need is this term should add up to 0 or cancel out, so that we have basically a constant times this psi. So why we selected these two terms? Because our two terms need to cancel out. There are three terms over here, only one term needs to survive, and you can't select the two negative terms because two negative terms cannot add up to 0, and also the energy is negative. And also we are given that this is 0 because we are given that this Bohr radius, this expression for this Bohr radius over here, we are given that this is because A naught is equal to 4 pi epsilon naught h cross squared over m naught e squared. So when you plug in this value, you see that these two terms actually cancel out. You can just plug in and see. So this means that finally just this term remains, which is minus h cross squared over 2 m naught a naught squared times e to the power minus r over a naught, and this is just the wave function psi. So what we see is that h psi equals to e psi, which implies that psi is an eigenfunction of the Hamiltonian with the eigenvalue E. The eigenvalue E is nothing but the energy. This is minus h cross squared over 2 m naught a naught squared, the term which survived over here, and plugging in the value of a naught, the Bohr radius, from this equation 3.65, we get the following. And simplifying it, we finally get this expression. This is the energy. So we have shown that psi is an eigenfunction, and we have found the value of the eigenvalue, which is the energy. Now we need to look at the last part of the question, which is to verify that the wave function is correctly normalized. And this constant term in the front is the normalization constant. So let us now look at normalization. So we need to evaluate this mod psi squared over the entire volume to find out the normalization, and this should turn out to be equal to 1 for a correctly normalized wave function. And integrating over the entire volume means that the limits of integration are given as follows. Psi is real, so psi star is also psi, so this is simply the following. And d cubed r, the volume element in spherical polar coordinates, is given as follows: r squared sine theta dr d theta d phi. So the phi integral is straightforward, that is simply 2 pi. And then we need to do this theta integral. This theta integral is nothing but 2, because integral of sine theta is minus cos theta, and when you put in the limits pi to 0, you get 2. So this makes it 2 into 2, 4 pi in the numerator, and now only the r integral is remaining. So here we'll make a substitution. Let r prime equals to r over a naught. So this gives dr prime equals to 2 dr over a naught, and in this substitution the normalization integral then finally becomes the following. So 4 pi by pi, that makes it 4 over a naught cubed. So r is nothing but r prime a naught by 2. So it is a naught over 2 r prime, and dr is a naught by 2 dr prime. Taking all the constants out, and this is nothing but the gamma function of 3, and which is 2 factorial, which is equal to 2. So this gives me 4, and a naught cubed cancel, so 4 by 8 into 2, which is equal to 1, which means that the wave function is correctly normalized. So we have completed the question. In this question we were given the wave function for the hydrogen atom, and we had to see that it was indeed the correct wave function by evaluating this eigenvalue equation, which is the Schrodinger equation, H psi equals E psi. Then we found out the energy, and we actually verified that this wave function is indeed normalized. So that was the problem. In the process, we saw the expression for the Bohr radius as well.